Imagine for a second that you just record a quick voice memo on your phone. Just like 3 seconds of you talking.
Right, something totally mundane.
Yeah, exactly. Maybe you're ordering a coffee or, I don't know, complaining about the weather. And you hand that 3-second clip over to an AI, and suddenly that AI can speak fluently in 9 different languages.
Which is already wild, but...
But it doesn't just sound like a generic robot wearing a mask of your voice, right? It actually captures your specific tone, the subtle breathiness of your laugh, your unique emotional nuance. You can make it sound absolutely furious in German or like heartbroken in Arabic, all from that one boring coffee order.
It really is incredible. I mean, it shatters our traditional understanding of what voice synthesis can actually do. We're moving from just, mapping sounds to genuinely synthesizing emotion from almost zero context.
And the craziest part for you listening is that this isn't science fiction anymore. So our mission for this deep dive today is to unpack this massive leap in artificial voice generation. A new model just dropped called ParrotSpeech TTS, and it is proving that this level of synthesis is actually here right now.
Yeah, and it's openly available, which is huge.
Right. It's an open weights model, freely available under a CC BY-NC license, so researchers are literally already tearing it apart.
Yeah, well, what's fascinating here is that this isn't just some incremental update. When they put it up against top-tier proprietary systems, specifically, ElevenLabs Flash v2.5 ParrotSpeech achieved a massive 68.4% win rate in human evaluations.
Wait, 68.4%?
Yeah, evaluated by native speakers for zero-shot voice cloning. It's a staggeringly high win rate when you consider the sheer compute power of the proprietary models it's going up against.
That is nuts.
It is. And they achieved this by relying on a highly detailed technical paper in this totally new architecture. It's a hybrid, autoregressive, and flow matching architecture. They basically looked at all the bottlenecks in traditional text-to-speech and just built a completely new kind of engine to bypass them.
Okay, so that is exactly what we need to figure out today. First, we're going to look at how the AI actually, hears and slices up audio using its codec. Then we'll get into that unique two-brain engine you just mentioned that generates the voice. And finally, we'll explore how they trained it to sound so undeniably human and run at lightning speed.
Sounds like a plan.
Okay, let's unpack this. Because to understand how the model generates speech, we first have to understand how it breaks speech down. To a computer, my voice right now is just what? A chaotic wave of numbers?
Exactly. Raw audio is just an overwhelming flood of data. I mean, a standard microphone captures 24,000 samples every single second.
Right, 24 kilohertz.
Right. And if you feed 24,000 data points per second into an AI, it's just going to choke. So the very first step here is the ParrotSpeech Codec. Its entire job is to compress that massive wave down into just 12.5 frames per second.
Okay, 12.5 frames. That's way more manageable.
Oh, absolutely.
Right.
And within each of those frames, the codec extracts exactly 37 discrete tokens.
Okay, 37 tokens per frame. But are all those tokens doing the exact same job?
No, and this is the foundational brilliance of the model, really. They divide those 37 tokens into 2 completely different categories. You have exactly 1 semantic token, and the other 36 are acoustic tokens.
Okay, let me try an analogy here. Think of speech like a live musical performance. You have the sheet music, right? The notes, the structure, the actual underlying meaning of the song.
Yes, the semantic meaning.
Exactly. So that is your 1 semantic token. But then you also have the sound of the instrument itself. The resonance of the wood, the acoustics of the room, the sharp intake of breath before the musician plays. Those physical sound qualities, those are your 36 acoustic tokens.
That is a highly accurate way to visualize it, actually. And by strictly separating that sheet music from the instrument, they achieve a remarkably low total byte rate of just 2.14 kilobits per second.
Wow, 2.14.
Yeah, I mean, older models like Mimi, which use a 16 codebook setup, require about 2.2 kilobits per second. So ParrotSpeech comes in even lower than that, but completely dominates them on all the objective metrics for audio quality.
Okay, so I understand how compressing it saves a ton of space. But wait, how does the AI actually separate the sheet music from the instrument? Like, if you just feed it a sound wave, how does it know which part of the wave is the meaning of the word coffee versus just the sound of my voice saying it?
That is the big question. And they solve it using a really brilliant technical trick called ASR distillation.
ASR?
Automatic speech recognition. So instead of relying on external forced aligners or, trying to teach the model human language from scratch, they just run the raw audio through a frozen version of Whisper.
OpenAI's transcription model.
Exactly. Whisper already knows how to understand language.
But wait, if they aren't feeding it the paired text transcript along with the audio, how does it actually map the meaning to the exact millisecond of sound? Like, how does it steal Whisper's homework without looking at the text?
It's basically looking at the internal math of Whisper. They use a combination of a cosine distance loss and a soft alignment matrix.
Whoa, okay, wall of math right there.
I know. Let me break it down. That soft alignment matrix is derived directly from Whisper's cross-attention weights via something called dynamic time warping, or DTW.
Okay, dynamic time warping, you're gonna have to ground this for me.
Right, so imagine watching a really poorly dubbed movie. You have the audio track and the visual track. They represent the same exact event, but the timing is just slightly off. The lips move, and then the sound comes a second later.
Oh, yeah, the worst.
Dynamic time warping is basically a mathematical way to stretch and squish the timeline of the audio until the peaks of the sound wave perfectly align with the visual movement of the lips, without ever changing the actual sequence.
Okay, so Parrot Speech is stretching and squishing its own semantic tokens, its own sheet music, until they lock in perfectly with where Whisper says the words are happening.
Exactly. It essentially steals Whisper's internal understanding of where words happen, and then it uses that cosine distance loss to force its own semantic meaning to match Whisper's meaning. It's incredibly elegant.
That is wild. It just implicitly learns it. So that handles the single semantic token. What about the 36 acoustic tokens? How does it compress the messy sound of a room?
The acoustic tokens are handled totally differently. They are quantized independently to 21 uniform levels using finite scalar quantization.
Wait, FSQ. So they force the infinite variations of real-world sound into 21 rigid steps.
Yes, exactly. Because human sound is continuous, if you force it into 21 distinct uniform levels, it severely limits the number of possibilities the AI has to calculate later.
Oh, that makes sense. It makes the math actually manageable. Okay, so we've got the blueprint. We know how the codec slices the audio up. But here's where it gets really interesting. Now that we know how it separates meaning from sound, how does it actually generate new, unseen speech from like a 3 to 25 second voice prompt?
This is where we get into that dual architecture, the two brains I mentioned earlier. Generating speech requires solving two completely different physics problems. The first brain is a decoder backbone based on the Minstrel 3B architecture.
Okay, Minstrel 3B.
Right, and this brain's only job is to handle the semantic tokens autoregressively.
Autoregressively, meaning it predicts the sequence one step at a time, like predicting the next word in a text. It just logically types out the sheet music note by note until it hits an end of audio token.
Precisely. It's perfect for maintaining long-range logical consistency.
But wait, if the autoregressive approach works so well for the semantic meaning, why not just use it for the acoustic sound details too? Why build a whole second system? It seems overly complicated.
It comes down to scale and the physical nature of sound. Generating 36 acoustic tokens per frame, step by step, is incredibly dense. If you use an autoregressive model for that, it becomes agonizingly slow and rigid.
Oh, because there's just too much data per frame.
Right. Sound isn't stepped in logical, like grammar, it's fluid. So for the 36 acoustic tokens, Parrot Speech uses a completely different second brain, a flow matching transformer.
Flow matching? How does that work?
Well, instead of predicting discrete tokens one by one, flow matching models a continuous velocity field. It takes a canvas of pure, random, static Gaussian noise and learns the mathematical trajectory required to transport all of that noise simultaneously into a detailed acoustic embedding.
Oh, wow. So if the autoregressive brain is like a typewriter, rigidly clacking out the meaning one letter at a time,
Yes.
then the flow matching brain is like a paintbrush. It sweeps across the whole canvas, taking that structure and washing all the color and texture and acoustic resonance over it at once.
That's a perfect metaphor. And the developers actually tested other methods for this, like mask GIT or depth transformers. But flow matching won out because it has a tiny per frame sequence length.
How tiny?
Just 3. Compare that to a sequence length of 38 for mask GIT. Because it's so small, it is far superior for compute latency and expressivity.
Okay, so we have this hyper-efficient engine generating semantic and acoustic tokens. But for you listening, think about those AI voices that start off sounding okay, but like halfway through a sentence, they sort of trail off or sound completely deadpan and robotic.
Right, the naturalness fades.
Yeah. So how does Parrot Speech fix that? Because generating speech efficiently isn't the same as making it sound naturally human.
That is exactly why they had to introduce a massive post-training step, direct preference optimization, or DPO.
DPO. We see that in text models a lot, like a taste test, right?
Exactly. They adapted standard DPO for the semantic tokens, but they actually had to create a brand new flow DPO objective specifically for the acoustic tokens. By doing this automated test pitting winner and loser pairs against each other based on strict metrics, they dramatically improve the model.
What kind of metrics are they judging it on?
Things like word error rate, which is raw intelligibility, and UTMOS v2, which measures naturalness. And the results of this DPO training were massive. For instance, it dropped the word error rate in German by an incredible 3.25 points.
Wow, 3.25 points just from the post-training.
Yep, and it fixed the exact issue you just mentioned. The pre-trained model had a tendency to taper in volume at the end of sentences, which sounds super robotic. The DPO taste test punished that behavior and completely ironed it out.
So it literally learned how to maintain breath support to the end of a sentence.
Yes. And it shows in the human evaluations. While API competitors like ElevenLabs v2.5 might win on some automated metrics, ParrotSpeech absolutely dominates in human evaluations. Again, a 68.4% win rate in zero-shot cloning across 9 languages, from Spanish to Arabic, high and low resource.
That is unbelievable. And there was something else in the paper that stood out to me. Implicit steering.
Oh, yes. This is crucial.
Because normally if you want an AI voice to sound angry, you have to explicitly type in like bracket angry bracket before the text, right?
Right, you need explicit emotion tags. But ParrotSpeech consistently beats both ElevenLabs models in implicit steering. That means the AI can read the emotion that is implied by the text alone without needing any explicit tags.
So if the text is, "I can't believe you did this to me," it just inherently knows to sound betrayed and angry.
Exactly. The autoregressive brain figures out the emotional subtext and passes that to the flow-matching brain, which paints the audio with anger. It's essentially acting.
That is mind-blowing. But okay, let's ground this for a second. We're talking about a massive two-brain system, complex whisper alignment, and DPO training. So what does this all mean for actually running the model?
You mean latency?
Yeah, exactly. If it's this complex, doesn't it take forever to generate a response? If a listener wants to use this as a real-time virtual assistant, it needs to be fast.
Well, the developers knew that inference and serving speed were critical, so they heavily tuned 2 specific parameters, NFEs and CFG.
Okay, let's start with NFEs. What are those?
Number of function evaluations. Think of it as how many computational steps the flow-matching paintbrush takes to turn the static into sound. You'd assume more steps means higher quality, right?
Yeah, more brush strokes, more detail.
Actually, no. They found the sweet spot is exactly 8 NFEs. Anything more yields only marginal improvements and actually regresses the word error rate.
Wait, why? Why does taking more steps make it worse?
Because it starts overcorrecting. If you force it to take, say, 16 steps, it starts picking up on microfluctuations in the noise and amplifying tiny artifacts. It effectively hallucinates acoustic garbage. Capping it at 8 NFEs keeps the sound clean and cuts the compute time down.
Ah, okay. That makes sense. And what about the other parameter, CFG?
Classifier-free guidance. It's basically a strictness dial. It dictates how closely the AI must adhere to the 3-second voice prompt you provided.
So if I crank that dial way up...
If you crank it up too high, the AI becomes terrified of deviating from your flat, boring reference audio. It kills its ability to act on the implicit emotions in the text. You get a perfect clone, but it's totally monotone.
So what's the sweet spot for the strictness dial?
Setting the scale to an alpha of 1.2 is ideal. It preserves your voice, but leaves enough room for emotional expressivity.
Okay, so they optimize the math, but you still have to run this on actual hardware. How did they engineer it for real-world serving?
This is where they brought in vLLM-Omni to eliminate what's called Python-level overhead, which is basically the communication lag between the CPU and the GPU. The developers capture the entire ODE solver into CUDA graphs.
CDA graphs, what does that do?
Instead of the CPU constantly handing individual instructions to the GPU step by step, a CUA graph pre-records the entire sequence. It hands the GPU the whole instruction manual up front.
So it just bypasses the middleman entirely.
Exactly. And that one optimization improved latency by 47%. It dropped the processing time from 133 milliseconds down to just 70 milliseconds.
So 70 milliseconds, that is instantaneous.
It is. And when coupled with asynchronous chunked streaming, which outputs the audio to your speakers before the full waveform is even finished, generating a single H200 GPU can serve over 30 concurrent users with a 0% wait rate.
And a sub-second time to first audio. That is just, it's an absolute masterclass in engineering. So just to synthesize this whole journey for everyone listening, we explored how the ParrotSpeech Codec separates the semantic meaning from the acoustic sound using that incredibly clever whisper distillation trick.
Right.
We saw how the hybrid, autoregressive, and flow-matching engine actually builds the voice from the ground up, how the DPO taste tests make it sound emotionally resonant, beating top competitors 68.4% of the time. And finally, how CUDA graphs make it lightning fast for the real world.
It's a massive achievement. And, if we connect this to the bigger picture, it leaves us with something really profound to think about based on this paper.
Sure.
Because ParrotSpeech can take a mere 3 seconds of completely flat, neutral voice prompt and, using implicit steering, generate a highly emotional, nuanced performance entirely based on the text.
Right, from almost nothing.
Yeah. So for you, the listener, this raises a fascinating question. If an AI can convincingly synthesize your deepest emotional resonance from 3 seconds of your completely unemotional audio, what does that mean for the future of digital authenticity?
That is the big question.
When we hear a recording of a politician or a loved one sounding furious or heartbroken, how will we ever know if it was truly them or just their semantic sheet music played back with an AI's synthetic acoustics?
Honestly, that is a slightly terrifying but deeply important thought to end on. That X-ray machine of truth we used to rely on with audio is officially broken. Thank you so much for joining us on this deep dive, and as always, keep exploring and definitely keep questioning what you hear.